All right, welcome to United Astronomy Clubs of New Jersey. We are here in Jenny Jump State Park in Hope, New Jersey. I want to welcome everyone who is not only here, joining us here, but also joining us online, because that is right, we do live stream these on Twitch and YouTube. So if you're ever can't make it out here and you're looking for something to do on a Saturday night, do feel free to join us online. It's free. Do hit those like and subscribe buttons. Say hi. Let us know you're out there. All right. So I know we just had a couple people come in and we're parking. So I want to give them a couple minutes to make their way on down here for the presentation. Couple things. I do want to encourage everyone to check out our website, uacnj.org. You're going to find a list of all, not only our upcoming talks, but past talks we had with links to view them. So if you're very sad you missed out on Chirag's presentation on the problem of space trash, don't worry. You can still watch it, and if you have any questions, hit those up in the comments section of that video. We have them saved on our YouTube channel. In addition, it's also where you can find information about all our member clubs, because UACNJ is actually United Astronomy Clubs of New Jersey, meaning we are a club made up of other clubs. And if you are looking to get into the hobby, one of the best and easiest ways is to join your local club, and we always want to encourage that. In addition, if you want to know great ways to get in touch with us, check us out on our social media, our Facebook, our Instagram. We have a Discord server, all great ways to ask questions. If you do astrophotography, share your images on our Discord server. Please do reach out. It's where we also post any upcoming events, any special fun things we're doing, such as the last presentation that we have in on site for the year and at the end of October. We encourage everyone to join us in costume because it is rather close to Halloween, and why not have some fun with it? So, with that, for those of you here, brief safety, well, of course, if you need to use the restroom, that is the porta potty in the back. To my left, your right, it is big, it is blue, it is illuminated slightly by red, and now someone else's flashlight. Just feel free to use that. We also have a little museum area and gift shop. Feel free to check out our display of meteorites. I do have someone in there tonight, which is great. They've finally realized I cannot be in two places at once. So, #winning. Hello? There we go. We also have each of the sheds you saw while driving in houses its own telescope. After the presentation, the ones that have the roofs rolled off are the ones that are open, and we have volunteers manning them. So do feel free to ask questions. They love questions, and sometimes they won't know the answer, but that's why we all now have portable internet boxes in our pockets, also known as a cell phone. When we go to leave here, for all of the adults who drove, please use your headlights. We do not want to get run over. I'm sure you feel the same way. No one needs those medical bills or paperwork. That being said, as we walk around, because it is a state park, it is in fact dark, do try and keep any flashlights, or if we're using our cell phone to move around, try and keep the light pointed towards the ground, just so we don't accidentally blind people needlessly. Someone had their latest and greatest, 100,000 lumen monstrosity from Amazon, and that killed my stargazing for the night. So try not to be that person. With that, you're not here to listen to me blabber on. You're actually here for Paul Fischer here, and he's going to give his talk on anatomy of a star. Paul Fischer has a Bachelor in Engineering and Chemical Engineering from Stevens Institute of Technology. Ooh, perfect. I needed some light. And has worked in the environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night, several years ago, lying in awkward positions on his roof, freezing cold because winter, and holding a pair of binoculars where he caught a brief glimpse of the Galilean moons of Jupiter. After that, it's history. He's hooked. We have not allowed him to escape his already read pile on the topics of astronomy, puts my to be read list to shame, and he's a consistent volunteer, current vice president of the organization. And with that, here's Paul.
Hi everyone, how you doing? Thank you. I didn't do anything yet, so but I'll take the applause. Thank you very much. As Kim said, tonight's presentation is on the anatomy of a star, which sounds more salacious than it is, because what are we talking about? Who, what, and why? First of all, who's to blame? I did a video course, or I didn't do the course. I just passively, watched the course from Alex Filipenko. He is has a doctorate and is a professor, and has done a lot of research on black holes and other cosmological topics. The specific course is Understanding the Universe, an Introduction to Astronomy. And also, I've perused a book from Kenneth Lang, The Life and Death of Stars, and this is where you can get that publication. So give these two gentlemen all the credit for tonight's presentation, and I'll take the blame for any mistakes you detect in the presentation. What are we going to cover tonight? We're going to cover an introduction to a particular star, find the inside scoop about that star, note that everyone loves an origin story, figure out what makes a star tick, or what we know, we being humanity, knows about what makes a star tick. How does our chosen star compare to other stars? And then finally, what happens at the end of that star's story. Introducing the sun, sort of. Why is the sun... before we get into that, we do get this question asked. Yes, the sun is a star, and other stars can be considered the suns of their own planetary systems. So sun and star, there's no real difference other than its relationship to us. However, we must be of two minds. Why? Because when compared with data from measurements of other stars, the sun is really kind of an average star and relatively unremarkable. In fact, if you were at all familiar with the HR diagram, it's a diagram of stars and where they exist in their mass and how much output they have. The sun is very nearly square, right in the middle, so very average. However, our sun is obviously emotionally, historically, geologically, and evolutionary and physically important to us. It's indispensable. We wouldn't be here without it. To us, it's the most important star in the universe. Why sort of? Why did I put that caveat, sort of, at that title slide? Well, astronomers are actually actuaries, and I said that sentence successfully. So now I've earned that applause you gave me earlier. Astronomers are actually actuaries. In other words, we look out into the universe, see stars in our galaxy, stars in other galaxies, etc. And we are seeing light from those stars as they appeared, however distance away they are in light years from us. So a star 100 years, 100 light years away from us, the light has been traveling to us for 100 years. So we are seeing that star now as it appeared 100 years in the past, in wherever it is currently. Our sun has been around for 4.6 billion years. Humans have been around for about 200,000. Modern humans. When looking at stars, astronomers not only have to take into account the speed of light and the expansion of the universe, but also their statistical variation. So what's happening is we have the sun and we make observations from it, but we're also making observation of a huge population of stars that could be beginning their life or ending their life or be somewhere in the middle. So we are getting this statistical variation, a whole universe of them. So, from a data point of view, it's awesome. What's not so awesome about most of the stars compared to the sun? How far away they are, right? We can't fly a satellite to any other star besides our sun. We have satellites currently orbiting the sun, taking data. We can't do that with any other star. So it's not a bug, it's a feature. So you take that statistical variation, which is awesome for science, that this universe of stars gives us, and you take the proximity of the sun and its convenience for actually conducting more meaningful experiments. I don't want to say more meaningful. It's not like we don't get meaningful data from studying stars, but we get to do more experiments that we couldn't do without the sun being so close. So it works both ways. Our star is sun-like. Our particular star that we're talking about tonight is a model that's very sun-like. It's maybe not a stretch to consider it every star. In other words, we take the data that we know from the sun, it being a star, and the data we know from watching distant stars come to life or die or be somewhere in between in their lifetimes. And now we can get an overall picture by smashing it all together into one model that we understand stars better because we can do both. Hey, buddy, I was told it'd all be pictures, right? Not just boring science on the text, text-wise in the presentation. So let's start here. The Solar and Heliospheric Observatory. If you search SOHO in your browser on, say, Google, you're going to get a lot of pictures of a neighborhood in New York City. So you got to include NASA in your search terms in order to get SOHO, the Solar and Heliospheric Observatory. So search SOHO NASA and you will find this particular website. Current of today, however, I didn't update it this year. For this presentation, so it's not the current is a sun earlier. I think this year is the last time I did it. You want to pick HMI. It's what you can see through a standard solar filter, and here it is. No, wow, 2022. I haven't updated it in a while. It's probably just okay. Here's 2023. 24, okay, so 3 years of data, but you can see sunspots. where is the sun right now? Man, look at the, wow, the sun went from a couple of sunspots to more sunspots to, still a good amount of sunspots. What's happening on the sun right now? Does anyone know what it's called? What's happening on the sun? Solar maximum, right? Solar maximum. All right, so the inside scoop. What's inside a star? The materials of construction of the sun are pretty simple. Hydrogen, helium, and metals. And we'll talk about metals in a second, but it's 71% hydrogen and 27% helium. And then it's 1.43 concentration, mass-wise, of metals. What's a metal? Astronomers consider anything that isn't hydrogen or helium a metal, which as a chemical engineer makes me mad a little bit, because obviously there's a whole heck of a lot of other elements, right, that exist. What's that? Yes, anything that is not a hydrogen or helium to astronomers, not to chemists, not to anybody else, but astronomers consider anything else that isn't hydrogen or helium a metal. Metals isn't really satisfying, is it? All right, here's the analysis of the sun's light. You can see these are absorption lines here. Let's see, no, I do not. Absorption lines very quickly in a spectra. So you have the sun here, and around the sun is an atmosphere, and in that atmosphere are many different compounds, and what's happening is the light is exciting the electrons from those compounds. Now, all the sun's from the center of the sun, all the sun's rays that are headed our way, come equally in its spectra in a continuous curve. However, what happens is that these compounds in the way, the electrons absorb some of that light and then re-emit it. But they emit it in a direction that wasn't towards your eye necessarily. It's only a small percentage chance that that photon being re-emitted is going to hit your eye. So what you get is this dimming at different frequencies of light, and those correspond, if you remember at all, orbitals and things like that from your chemistry classes. So when a electron jumps or descends in an orbital, it'll give off or receive a photon. And that's what happens. So that a photon is emitted in a different direction, so you get a dimming in that frequency, and that corresponds to different compounds, because those all happen at specific frequencies for specific orbitals. So that's what a spectrum is. And this is an analysis of our sun's light right here. Here is a plot. You can't see it, but all the elements are by atomic weight are along the x-axis. Along the y-axis are the logarithm of how much of that stuff is in the universe. And here's why astronomers are a little quirky in their definition of what metals are versus helium and hydrogen. Here's helium and hydrogen. Way up here, 2 orders of magnitude higher than even the highest of any other element. Why? What big thing happened that created all that hydrogen and helium? The Big Bang. That's why our universe is made up of mostly hydrogen and helium. That's why astronomers are a little kooky in their definition. All right, then we go down here many orders of magnitude below hydrogen and helium, and then we slowly drop off here until we just about level off right here in the higher atomic weight elements. What's happening here? What are these elements? Those elements are all created in stars. So we have an ongoing, trillions and trillions and trillions of ongoing factories in the universe making these elements. These elements and these elements are all at about the same level. They are not being made in stars. They are being made in other cosmic nuclear reactions throughout the universe. High energy explosions, interactions with cosmic rays, very energetic cosmic rays. Those type of things are making those elements. This stuff is being made in stars, which again kind of reflect what's going on here in the atmosphere of some stars. So these are metals, the ones that are several, if not many, orders of magnitude below the concentration of things in the universe that was created in the Big Bang. So let's play a game and understand some of the units of, or some of, like how intense are things at the sun. The core temperature in Kelvin is 1.56 times 10 to the 7th degrees Kelvin. That's pretty hot. 10 to the 7th means, you know, many zeros, 7 zeros. Just on Earth, what does Kelvin mean? What's 0 Celsius, the freezing temperature of water in Kelvin? 273 degrees. So many zeros above that. Core pressure is 1.97 times 10 to the 11th atmospheres. How many atmospheres are we experiencing right now? 1. So that's how much. That's how big that is. The mass in kilograms is 1.9884 times 10 to the 30. I'm trying to lose weight right now, but if I had to lose that this amount of weight, that would just be I'd give up. Diameter in kilometers is 1,391,400. The distance from our from Earth to the Sun is 1.496 times 10 to the 8th kilometers, and the distance in astronomical units is 1. When you see a number as simple as that, what's your mind thinking? It's the definition of the unit. The definition of the unit is from the sun to the earth. The astronomical unit is the distance from the sun to the earth. How much is this in miles? You know, I expressed it in kilometers. How much is that in miles? About 93 million. Thank you. Distance in light years is 0.000016, and the energy it puts out is 3.828 times 10 to the 26th. What does the sun drive? How much of the Earth's energy do you think the sun drives? Is responsible for? 100%. Anything here that has energy, except for some nuclear reactions, comes from the sun. All the power of Niagara Falls comes from the sun lifting up water, putting it at an elevation above Niagara Falls, and letting it fall down again. So we think we are awesome in our ability to create power. We ain't nothing. All right, the sun is putting out, the sun drives everything on the planet. How about volcanoes? Volcanoes is still coming from, so again, some nuclear reactions, right? Some of the heat here we experience on Earth is due to nuclear reactions, leftover uranium and things like that in the Earth's core. However, a lot of it is due to the sun. We're getting bombarded constantly by the sun. The sun is stressing the Earth with tidal forces. What's but that's all powered by something, right? The Earth doesn't generate that. The Earth is not a generator of energy. So some nuclear, but a lot of it, most of it that we experience anyway, is from the sun. So what's in the sun really? What really is that stuff? We talked about elements, we talked about other things, but what is that stuff really? It's really incredibly hot, the sun is incredibly hot, incredibly massive, and under gargantuan pressures. It is not made up of matter that we normally experience it. It is made up of a fourth state of matter called plasma. Everyone's familiar with gas, liquid, and solid. Plasma is another phase of matter. What plasma mostly is, in the sun anyway, is hydrogen nuclei, protons, and free electrons. Electrons that have not in orbitals anymore, are completely disassociated from their parent atom, from their nuclei. Plasma is a fluid. It's evenly, even if it's extremely dense at the core of the sun. So that really dense, that really high pressure really squeezes that plasma down. It's still a fluid. The average density of the entirety of the sun, if you do the core all the way out to its atmosphere, is about 1.41 grams per cubic centimeter. That's actually very close to 1, which is what's 1 gram per centimeter? What fluid is 1 gram per centimeter here on Earth? Water. So the entirety of the sun is about the density of water. But it obviously goes through a huge variation depending upon how close you are to the core. At the core, it is greater than 10 times the density of lead. So here's a solar structure. Further information about the inside of the sun. You have a core. You have a radiative zone in our sun, a convective zone in our sun, and you have the photosphere, the chromosphere, a coronal hole, which happened about a week ago, the corona, which is the halo here around the sun, and you can see flares and prominences, a flare on the sun or a prominence coming off the limb of the sun, and you can also see those sunspots that we were seeing on the SOHO satellite images. So that's, kind of what's inside the sun. The interior structure is revealed by helioseismology, which is a lot like seismology here on Earth, where we measure earthquakes and we actually track them through the Earth, and we can tell some things about what's inside the Earth through the tracking of that seismology. The same thing happens with the sun. We can see a disturbance on the surface, track what it does to other parts of the sun, and understand a little bit about what's happening with density and other things in the core, because we can predict its shape of the whatever energy was given off by that disturbance, and predict a path to see something on the other side of the sun, And if we see it, then we know, our predicted path is correct, and we can make deductions about what is happening inside the sun. Okay, also the sun, again, this is a model for all stars. Our sun that I'm talking about, our model sun, is a magnetic dynamo. Here, through the poles of the sun, you have this magnetic field happening at solar minimum. Let's say, call this the quiet state of solar minimum. Is the quiet state of the magnetic field of the sun. So the magnetic lines are going basically straight across the not radii, but great circles on the sun. Well, what happens here is the sun does not just sit there. The sun is actually circulating, and the sun circulates faster at the equator than it does at the poles. So the lines start stretching like this. So we started with at solar minimum, these nice, crisp, up and down magnetic lines, and they start getting pulled because the equator is traveling faster than the poles are. And so those magnetic lines start getting pulled, and then they start doing loop-de-loops and crazy things at solar maximum because they get pulled so far. They start attaching to each other and twisting up and all those type of things. So that magnetic dynamo is what causes the solar cycle, which is how long? 11 years about. And it is and remember, a cycle goes from one state all the way back to that state again. So it's from solar minimum to solar maximum back to solar minimum again is about 11 years. 11 years long. It was originally discovered by recording the frequency of sunspot activities, flares, sunspots, CMEs, coronal holes, and other solar surface and atmospheric phenomenon are all vary with the solar cycle. It's important to study and predict solar events and the space weather to protect infrastructure, satellites, and astronauts. Not only do we have the possibility of seeing a corona in the north, but we have some business to attend to because modern civilization runs on many of these things, and we need to protect those things from the space weather. All right, so that's the inside workings of a sun, of our sun, the model, and our sun here in our solar system. A star is born, so how cute. We have baby stars here we're going to talk about. So please be very quiet for the next few slides. Don't wake the babies. Right here is a stellar nursery. Here's other stellar nurseries. This one's the Lagoon Nebula. You notice what these, this is the Great Orion Nebula, I believe. And I don't remember what this one is. Another nebula. All star-forming regions. And here are young stars, but these are not babies anymore, so I guess we can talk louder again. These are young adults starting a family, and these are planets starting to clear their orbital paths around around those suns. And these are actual pictures of images of newly born stars or young adult stars. What is a stellar nursery? You saw those pictures. It's a cold, dense, massive nebula, clouds of gas, of molecular hydrogen, mostly molecular hydrogen. Some helium in there too. Cold means about 10 degrees above absolute zero. So 10 degrees, absolute zero, if you remember me talking about Kelvin before, absolute zero would be 0 on the Kelvin scale. Cold means about 10 degrees above that, so 10 degrees Kelvin. Massive means about 10 these clouds are tens of light years across. Remember, the distance from the sun to the earth, 93 million miles, was 0.00001 something, right? Or 10 to, it was 10 to the minus 4 magnitude. So these are 6 times tens of light years across. I don't know. These are, yeah, 5 orders of magnitude larger than that. Those clouds are, the size of those clouds are required because the inside needs to be protected from disruptive cosmic radiation. Regions in that cloud, if they are protected, can then collapse spontaneously if they meet the Jeans mass. All that means is there is a number of required density. Meeting that required density, general gravitational attraction between all the dust particles in that cloud, they start interacting by being mutually attracted to each other, and they start collapsing. That collapse can sometimes be assisted by perturbations from external events. Of course, it can assist or it can destroy a star that is a region of gas that is spontaneously collapsing. But it can be also assisted by external events such as a passing star, a nearby energetic event, or a cloud collision. Okay, so once that collapse begins, that gravity is just going to keep on going. So once that gets to right before a star is actually born, a protostar, what they call a protostar, is formed. What is a protostar? It's a star heated by gravitational collapse, but it hasn't yet started nuclear fusion. Remember the conservation of energy, it's the law. So as all these particles start combining from a gravity, in a gravity well, if you remember holding something aloft in a gravity well, it is filled with potential energy. If you let it go and allow it to collapse, if you let a potential energy go, it starts turning into what's that called again? Kinetic energy, right? And kinetic energy is the same as heat. So the potential energy gets converted, and kinetic energy, the bulk motion of the gas, increases. Enthalpy, heat energy, and pressure energy therefore increases. It's getting hotter as it collapses. If the protostar is massive enough, eventually hydrogen fusion can be sustained. So it keeps on gaining energy, as these light year size gas clouds collapse into a protostar. And once a tremendous amount of energy from that tremendous amount of material ends up eventually lighting off hydrogen fusion. Once the hydrogen fusion gets lit off, that it can be sustained by that gravity continually trying to collapse that gas. But the collapse is halted by that fusion. The hydrostatic equilibrium is reached because you have the gravity collapsing and the fusion trying to push out. Once that happens, a new star is born. So hydrostatic equilibrium is really a fight between two opposing titans. Plasma pressure pushes out, gravity pushes in. but why is it stable? So why is this nuclear reaction going really stable when all it has is gravity pulling it back in? Well, remember, a collapsing fluid heats and an expanding fluid cools. Changes in the rate of the fusion are opposed by changes in the plasma expansion. So if somehow the fusion kicks off a little bit more, right? It just some sort of variation happens in the core. That'll push the gas out a little bit, and then the entirety of the sun will cool a little bit because that gas has been pushed out. It falls back, and when it cools, the fusion goes down, and it begins to collapse a little bit further again, which kicks the fusion back up again. So you can see it's self-regulating, which is why it's stable, which is why suns last hundreds of millions or billions, or even the smallest ones that are true suns, true stars, the smallest ones can last trillions of years. What is nuclear reaction? What are these nuclear reactions? First of all, this is a plot, a maxim. Sorry, let me try over here. Getting some interference. This is a Maxwell-Boltzmann distribution. This is the distribution of the kinetic energy in particles in, say, a sun. And then it has an activation energy here at this point, where particles, a lot of the particles don't have the required energy to create a fusion reaction. But a certain amount above this above this activation energy point here do have the required, these smaller number of particles have the required energy to create a fusion reaction when they impact. Here's the problem, though. This theoretical point here is opposed by the fact that the particles colliding are the same charge. So why? And they did these calculations, and they found that the energy on this theoretical point is actually much higher here, and we wouldn't have any stars if something else isn't happening, because it not only does it have to meet the energy requirement to kick off fusion, but in order to meet in the first place, they have to overcome the repellence, if that's a word, the two particles repelling each other because they are like charges. Positive doesn't like positive in electric charges, right? So why do we have fusion in stars, and why do we, is fusion happening? Well, sometimes it's a head scratcher, and we have to go to quantum physics, right? The electrostatic repulsion of like-charged particles would dictate a much higher thermal energy, as I just described. However, the smallest matter is quite weird. Particle physics is really weird and really hard to imagine. Remember, they can behave like waves. Small particles can change their position without moving through space. They, quote unquote, teleport to the new nucleus. So quantum tunneling, all that weird physics, is real, because otherwise we wouldn't have nuclear reactions without them. So the particle doesn't go like this. It starts here, and without traveling through space, winds up here. Quantum tunneling. Kind of looks like a teleport to us big beings, as opposed to someone who's small enough to be a particle. The higher kinetic energy a particle has, the more likely it is to tunnel. So quantum tunneling is required to make fusion go. Just an interesting thing how all the sciences are interrelated and how many things, why we need to understand those many things in order to understand how things are happening. All right, so the conversion, remember E equals mc squared. So what's happening in fusion is that 7 million, is that million? 700 million metric tons of hydrogen is converted to helium per second by the sun. That's a lot of metric tons. 700 million metric tons of hydrogen converted per second by the sun. That ends up in about 5 million metric tons of matter gets converted to energy. So E equals mc squared is actually telling us the conversion. So 700, this 700 million hydrogen goes to helium. That's a no-brainer. We know that the sun makes hydrogen into helium. That's the fusion reaction. What we didn't know is that when it does that, 5 million metric tons of that 700 million tons disappears, or not really disappears. It goes into energy. So the hydrogen going into helium results in a deficit of weight of helium. The helium is lighter than the hydrogen that was combined to make up the helium. The sun is, so why at these extreme amounts of conversions do we actually still have a sun 4.5 billion years later? Well, remember that we have 27 zeros at the end of the weight on our the mass of our sun. So it would take billions of years in order to get rid of that mass at this rate. There's enough material in the sun to go on for about another 7 billion years. Here's the actual reactions, the reaction mechanism for our sun. That's 4 hydrogen nuclei go to 4 helium nuclei plus gamma radiation. And does anyone know what that is? Neutrino. Thank you very much. Neutrinos. So here are the actual steps in the mechanism. We don't have to go into much, but there are what they call various isotopes that go into the mechanism that are required to happen in order for the whole overall reaction to happen. That isn't the only nuclear reaction that happens in stars. Just so you know, larger stars go through this reaction. It requires metals in the reaction in order for it to go. So larger stars are a little bit different than the sun. And what's the difference between this one and this one? Typically when you have competing reactions in something, one of them is faster than the other, and the conditions in a larger star make this one the dominant reaction, and the conditions in a smaller star make this one the dominant reaction. It's not like it's completely exclusive necessarily. A little arithmetic. The atomic weight of hydrogen is 1.00747 grams per mole. The atomic weight of for helium is 4.02602 grams per mole. 4 times 1 hydrogen is 4.02988 grams per mole. Look, the 4 of these does not equal the helium nucleus. That's interesting, isn't it? Or the atom. So there is a deficit, and that's the deficit I just told you about. So when fusion happens, energy is given off, and that is just mass being converted to energy. Very interesting. Our sun has class. What we can and can't know about our sun, we cannot know the size of stars or their luminosity from knowing their brightness. How bright stars are is not sufficient for us to understand anything about them. We have to know more. Light's brightness depends upon distance. It has an inverse square relationship. So a star that is bright might be close to us, or it just might be high luminosity star, a star that's putting out a lot of energy. Stars' luminosities can be classified by a unit of power like watts or absolute magnitude. There is, language that says that we're talking about the luminosity or absolute magnitude, which is just a brightness that is defined at a set distance from a luminous object. So you have to be careful that when you're talking about the brightness of stars, whether you're actually talking about the brightness as we're perceiving it at our current location or its inherent brightness or luminosity. What we can know from the light of stars, we can know that black bodies irradiate with color intensities with a predictable curve. We know that the curve shape, we can predict the surface temperature of the star. Knowing the surface temperature of spectral type and luminosity class, we can know the star's masses, and knowing a star's mass lets us know many things about a star. So we have to know a bit about how black bodies, how things that irradiate light inherently as opposed to reflecting light, how they, what those curves look like, and we do know that. These are black body radiation curves. Again, this is a spectra that we were introduced to earlier. So we have these curves that can help us know all that information by seeing the spectra coming off of stars, which behave as black bodies because they produce light and heat and other radiation. They produce a lot of radiation, but they produce visual light. This is the visual light range here also. And we know it from these curves. All right, and so we know that the dominant lines in various class stars equal various temperatures of the atmospheres of those stars. And right around here, there's a yellow-white star between G and F. I think it's closer to G. And here the sun is a G2V star. So we're right in between. We're at like 6.5, I think, something in that range. So we're right close to the edge here. The tail of the tape. These are various, oh, I'm sorry, 57. I must be thinking of a different star. 57, so, but still, right close to the edge here. Right in the top of G is where the sun is. G-type star. These are other stars that you might have heard of. Sirius, Vega, Aldebaran, Polaris, Rigel, Betelgeuse. These are their temperatures. These are their radii. These are their masses. And these are their luminosities, which we can get all that information from these curves because different masses equal these different temperatures here from these different curves. So you take all that information and you plot the different stars out on a, these are all, you can see this isn't cloudy. These are all different points. These are all different stars plotted on this Hertzsprung-Russell diagram, an HR diagram. These are actual stars, and the sun is at 1. The sun's right about here. It's a G2V star. There's other luminosity classes. Let's talk about these other curves. So any star that is along this, you see all these stars here, right? Any star that is along here, along this path, is what they call the main sequence. So our sun is a main sequence star. These are giants, supergiants, and hypergiants up here. Giants and these other stars are all end-of-life stars. And these are white dwarfs down here. And these white dwarfs are stellar remnants. All right, we're almost at the end here. Red giants and supergiants. When the sun goes up, uses up its hydrogen fuel, it will collapse until its core gets hot enough and begins to fuse helium to carbon and oxygen. It'll then rebound and expand. More massive stars will repeat this process, where our sun will instead of just having a helium core, it'll have a helium and carbon and oxygen core. More massive stars will even go further. They'll have neon, magnesium, silicon. These are all concentric active cores found in massive stars. So they start to build on each other. Successive fusion types require hotter temperatures and give off more energy. The sun or star will expand to become a red giant or a red supergiant. Regardless of the mass, fusion stops at iron. Iron fusion doesn't happen. It begins, but it's endothermic. You put more energy in to make it happen than it gives out, which will kill that hydrostatic equilibrium. Once fusion stops, hydrostatic equilibrium is gone. The sun or star will continue to collapse until something stops it. For some reason, my microphone doesn't like that position. So what besides fusion stops a star collapse? So this fusion is now ended. It's out of fuel, or it hit iron, and it ended. Electron degeneracy holds up white dwarfs. That's particle physics again. What is electrical? Just think electrons don't like each other too much. And now you're trying to really compact them together because that fusion isn't happening anymore, so the gravity just continues crushing and crushing and crushing. The only thing holding up white dwarfs is the fact that electrons don't like each other. Particles with like quantum values must stay separate. It's the Pauli exclusion principle. The free electrons in such a star order themselves and provide a back pressure to resist the gravity. If the electron degeneracy isn't sufficient, then something else happens. The star continues to collapse. Even that electron degeneracy, even those electrons repelling each other, have an upper limit to how much force they can hold up. The next thing to happen is that all particles in particle physics are subject to this exclusion principle. Neutron degeneracy now holds up neutron stars. So we're off of white dwarfs, and we've collapsed now to a neutron star. Exactly like electron degeneracy, neutrons are excluded from the occupying like states. Neutron stars, however, have an assist that electrons did not. Because we are talking about baryonic matter, now we can apply the strong force, which can be a repelling force depending upon how far away the particles are from each other. give an assist to the Pauli exclusion principle. And so the neutron stars are denser because they've collapsed further and they got caught by a higher level resistance force that is the strong force along with the Pauli exclusion principle. However, that also has an upper limit. And the gravity, it could just be the star is so massive that there's so much gravity, can be higher than that. So beyond those two opposing forces, I've got nothing to offer that could resist that collapse, and neither does the rest of the universe, it turns out, because that star remnant will continue to collapse and will form a black hole. So those are your three fates of a star reaching the end of its life. A white dwarf, a neutron star, or a stellar black hole. Here are two examples. This is the Crab Nebula, supernova remnant with a neutron star in the middle. And this is the Ring Nebula, which you'll probably see tonight, with a white dwarf that you can see right there. This is another supernova remnant. So I talk a little bit more about black holes in a black hole presentation. So I sort of left these cool images as a teaser. We will end our talk on stars there. So please look to that presentation, or I can ask any questions you might have about that. But that's how stars go. And like I said, definitely you're going to see the Ring Nebula tonight in a telescope. Kind of cool. It is a white dwarf. It is the atmosphere of a star thrown off into space, and the core of the star collapsed down to a white dwarf. Kind of cool. All right, everyone, please consider joining an astronomy club to see more of this stuff. And everyone, please stay safe tonight. Use caution when navigating moving cars and in the darkness.
All right. Thank you, Paul, for another great presentation. So, I'm sure a few of you have questions, so we will be doing a question and answer session. That being said, I did see a few of you sneak in during the presentation, and the safety briefing is unescapable. I must give it to you. So, with that being said, if you need the restroom, that is the porta potty in back to my left, your right. It is blue and it is illuminated by red. We also have a little museum area and gift shop. Feel free to check out our displays of meteorites and other cool stuff. When you came in, you must have noticed the sheds. Each houses its own telescope. The ones with the roof rolled off are open, and we do have volunteers manning those.
The Greenwood is open, so they're not only are the ones
one behind the house too. We also, when we are going to leave, we are using our headlights. We do not want to get run over. We do not want to see people get run over. It's quite frankly way too much hassle. That being said, any flashlights, as it is quite dark in the state park, do keep those pointed down. So how questions are going to work is if you have a question, you're going to raise your hand and wave it about. I am the Jurassic Park T-Rex, and I cannot find you in the dark unless you're moving. Hazard of staring at a screen. Online people, you can just type your question. Were there any questions?
I think I heard someone saying
Okay.
right here.
Oh, yeah, I was trying to figure out whether that was the scouting group needing to be there, or you had a question, right? Okay, if you want to just...
So, like, what would it take
hold the mic.
So I remember him talking a lot about how a star would die, but, like, what would it take to reverse the chemical reaction from from hydrogen to helium, like, to reverse it? Or is that even possible in the first place?
Well, what is the reverse reaction, nuclear reaction of a fusion reaction called?
Fission?
Fission. So
Ooh, I know one.
now, the fission reactions that I'm aware of are high atomic weight particles that are inherently unstable. So I imagine there are theoretical ways of doing it, but I don't know whether they're at all practical. I am an amateur astronomer, not a nuclear physicist. So
And a chemical engineer, also not a nuclear
a
physicist.
chemical engineer, not a nuclear physicist. So you would have to ask a nuclear physicist that particular question. But I imagine there are theoretical limits associated with that, and whether it's ever possible or even energy efficient enough for that reaction to go, I don't know. But it's definitely worth pursuing. It's a good question. I just don't know the answer.
Right. I'm gonna get to you just in a minute. Our online question I see is, could we send a newer satellite to try and see how far it reaches, like we did with the Voyager probes? And if we did, would it reach farther than said Voyager probes?
Yeah, it's difficult to purposefully design a mission to do that, because that mission is currently what, 50 years in, and they just don't fund things 50 years long necessarily. That we are continuing to put money in and continuing that, but those missions were never planned to go that long, so I don't know whether we could ever plan a mission specifically to go 50 years. And those objects are really going pretty fast, getting most of their energy from slinging around planets. I don't know necessarily whether we can put something like that out there. However, they do have some proposals for visiting stars. So we have for very small probes driven by an earthbound laser, but that's all in the conceptual stage and is nothing like putting real technology down on the ground to do that yet. So theoretically, it's possible to do something like that, but I don't think that we are actually planning a mission where we're putting a satellite like Voyager out all the way at the end of the universe again. I mean, the end of the solar system.
All right, we got another question out here.
So in the equation E equal mc squared,
Yep.
isn't it more like E equal mc squared plus neutrino? Because I saw that the mass defect is more than energy generated.
Well,
So-
it depends upon where you draw your box, right?
Yeah.
So when you talk about any energy or mass system, you have to draw a box around the system. And so are you excluding the neutrinos from the energy calculation, or are you including the neutrinos in the energy calculation?
But
So if you include the neutrinos
yeah,
in your energy calculation,
yeah.
then you don't have to have a neutrino term in your energy balance, right? In your energy mass balance. So if you
But it doesn't balance. Like so E is including neutrino. You are saying E includes neutrino, but neutrino is particle with mass. So shouldn't it be E equals mc squared plus neutrino? Neutrino energy or neutrino kinetic energy.
okay, do neutrinos have mass?
I think so. Yeah.
I think they have a theoretical mass. I don't know
Yeah,
whether
yeah,
we
yeah.
know they. I don't know that we've measured that. Have we measured the neutrino mass yet?
I think there is science to try and learn more
I
about
think we've
them.
inferred that neutrinos have mass because
Yes.
they are not particles that are traveling at the speed of light, and that
Yes.
they are not, and that right, if you anything traveling at the speed of light does have to is immortal, right? It does. It's not subject to time.
I mean, the motivation of inventing neutrino by Wolfgang Pauli
Yep.
was because E equal mc squared
Right.
didn't quantitatively valid. So some to match the energy.
I understand what you're saying.
Yeah.
And I understand your argument. Yet the standard mass of particle, the standard energy of creation of particle energy remains E equals mc squared. So evidently your question is beyond my understanding of it. So I would say that you would have to consult a particle physicist to get a robust answer to your question. I myself don't understand why the neutrino aspect is not considered a separate term in that energy mass balance, but it isn't. The conversion energy remains E equals mc squared, at least to my very basic understanding of it. However, you yourself might know more, or a particle physicist, if not yourself, might have a more robust answer than I do.
I would suggest reaching out to a couple universities with that question, specifically the physics department.
What is your background, sir? Computer science.
All right.
Okay. So again, there are people who are expert in this field. So you should probably consult somebody. That level of detail is probably better addressed by a nuclear physicist.
Right. Online people, if you have any last minute questions, do get them in. I wanted to get that in before I got back on that, just so that we can get it, not miss any questions. Did you have another question, or? Yeah. Okay. Right. So I do want to thank everyone who has joined us not only here, but also online. If you happen to be online, do remember to hit those free actions like, follow, subscribe. There are some not free actions, and you don't have to hit those, but if you do, we greatly appreciate it since we are a nonprofit organization. And doing so does help us pay our bills and keep offering the free public programs that we do. Looks like we are clear with questions online. So I want to, like I said, thank everyone. Thank you, Paul, for another great presentation. And with that, good seeing and clear skies.
Thank you.